So, welcome to lecture series on advanced linear algebra. Friends, we have already learned one interesting results about the decomposition of space as well as operators. That is, if T be a linear operator defined over a finite dimensional vector space V, which is also defined over the field capital F, then the space can be decomposed as a direct sum of invariant subspaces, and the operator T will also can be decomposed by finite number of operators, which are basically restriction of the operator T to invariant subspace, which is basically primary decomposition theorems. Today we are going to apply this concept in different places. First, let me consider the applications of these theorems in solving initial value problems. So, let us quickly recall what is initial value problem. So, initial value problem. Consider a system of equations dx by dt equal to ax, where capital X equal to x1, x2, xn, and x is function of t. I mean, each xi is function of t. Capital A is n cross n matrix over the field capital F, along with x at, I can say T naught is equal to say x naught. The star and double star is basically gives an initial value problem. Consider capital A is independent of T, that is star is an autonomous system. So, in this case, to find the general solution of the system star, since A is a n cross n matrix, I mean capital X belongs to n dimensional space. So, I will have n linearly independent solutions of the star. So, the general solution must consist of n linearly independent solutions. While finding the solution in our theory of ODE, we have seen that we have used the concept of generalized eigenvector. So, you will see that the primary decomposition theorem is used there to find the general solution of the system star place, specifically when system is autonomous. Now, let me consider one small examples. Let capital A equal to -2, 1, 0, -2, and capital X is a two dimensional vector. So, let me consider x1 and x2. So, we have d capital X by dt equal to -2, 1, 0, -2 and x1, x2, which is equal to Ax. We have already seen, we have already studied on theory of ODE the solution of this type of system is of the form of, say, capital X is a solution, then it is of the form of e to the power lambda t into some unknown function, say u, which is vector place. Let capital X be a solution. Then we have dx by dt equal to how much? Lambda times e to the power lambda t into u, which is equal to lambda times capital X. So, we have lambda times capital X is equal to, it has to be x. So, this implies a into e to the power lambda t into u must be equal to your lambda times e to the power lambda t into u, or e to the power lambda t into a minus I into lambda, this into u equal to 0. E to the power lambda t not equal to 0. So, this implies a minus lambda I into operating on u must be equal to 0. So, e to the power lambda t into u will be a solution of star provided u is an eigenvector, provided 0 not equal to u is an eigenvector associated to eigenvalue lambda, value lambda of A. So, first I have to find the what are the eigenvalues of this matrix first. We have eigenvalues of A equal to minus 2, 1, 0, minus 2 is a triangular matrix, are minus 2, minus 2, because the diagonal entry will be the eigenvalues of the triangular matrix. So, that is why minus 2, minus 2. So, what are the eigenvectors? So, for eigenvectors, we have A minus plus 2i operating on, say, some u equal to 0. So, this implies 0, 1, 0, 0 operating on x and y if I consider equal to 0, if u is equal to, I have considered suppose x comma y transpose. So, this implies that y equal to 0 implies I can consider E1 equal to 1 0 is an eigenvector of A associated to lambda is equal to minus 2. So, this implies I can consider the one solution x1 t equal to as e to the power your lambda t into u, which is equal to e to the power minus 2 t into 1 0. So, this is the one solution. Okay, at t equal to 0 I am getting simply 1 0. So, which is non-zero vector place. Okay. So, this is one solution, but we need another solution also, another which is also linearly independent, and then linear combination of the two solutions will give the general solution of the system x dash is equal to A x. Let me consider, let x 2 t is equal to t into e to the power lambda t into u plus e to the power lambda t into v be the second solution. How to know whether this will be the second solutions, how to guess what will be the general solutions, all these things. So, this I will discuss later on please. For time being you allow me say x t equal some function like this. Since the lambda is eigenvalue minus 2 is repeated twice. So, using the theory of OD for the single variable case, based on that spirit, if e to the power lambda t is 1, then t into e to the power lambda t will be the other ones. So, based on that spirit I am writing that x2 second solution as t into e to the power lambda t into some unknown function u plus e to the power lambda t into some unknown function v. Here I will consider u is equal to that is u1 which is equal to 1 0, u equal to u1, that is the eigenvectors associated to lambda equal to minus 2. Anyhow, so I have written like this. Now again, if this is the solution of this differential equation x dash is equal to ax, it must satisfy the equations. So dx2 by dt equal to how much? This is equal to I am getting e to the power lambda t into u plus lambda times t e to the power lambda t into u plus lambda times e to the power lambda t into v. Suppose this is the first one, then this must be equal to again a into x2. So, that will be equal to t into e to the power lambda t into u plus e to the power lambda t into v, these two. So, I will have a into t e to the power lambda t into u plus v e to the power lambda t will be also there, okay, must be equal to e to the power lambda t into u plus t into lambda e to the power lambda t into u plus lambda times e to the power lambda t into v. So, comparing the coefficient of t to the power lambda t and e to the power lambda t, I will have from the both sides. So, au equal to lambda u, this is one, and then other one I am getting coefficient of e to the lambda t as av equal to u plus lambda v, u plus this one. So, this implies au equal to lambda u. See, I told you that I have to consider u as a u1, eigenvector u1. The justification is coming from this. So, if I consider this is third equations and this is fourth equations. So, third, this implies that u must be eigenvector associated to lambda. So, which is already calculated or it is known please. The second function is v. So, that is satisfying the fourth equations. So, this implies that I am getting a minus lambda times I operating on v equal to u. So, the fourth equation can be written like this thing please. So, this implies that a equal to known, that is minus 2 1 0 minus 2 minus it will plus 2 into your identity 1 0 0 1, this operating on v. Say let me consider is equal to say v equal to y1 y2, this vector must be equal to u is equal to already known 1 0. So, this implies that if you simplify it, I am getting what 0 1 0 0 into y 1 y 2 equal to 1 0. So, this implies y 2 equal to 1. So, I can consider E 2 is equal to 0 1 transpose, which is equal to V please. Then I am getting V is also linearly independent to U please. I am getting two linearly independent vectors U and V, and we see that A minus lambda I operating on V is not equal to 0, because that is equal to U, which is not equal to 0, but A minus lambda I whole square operating on V equal to 0. Why A minus lambda I square operating on V equal to 0? Because for this polynomial, the characteristic polynomial is exactly equal to the minimal polynomial, which is equal to x minus lambda whole square. So, this means that here lambda is equal to minus 2. So, therefore, any element in the space of F2 will be basically annihilated by A minus lambda I whole square. Okay, so, that is why A minus lambda I whole square operating on V equal to 0 here. And so, I can write down, so my second solutions x 2 t is equal to what? X 2 t I have written, it is basically t into e to the power minus 2 t into u 1, that is your 1 0, plus e to the power minus 2 t into 0 1. So, this is my second solution please. Now, you see as t equal to 0, I am getting x 2 0 is equal to the vector 0 1 and x 1 0 equal to vector 1 0, both are independent to each others. So, therefore, x 1 and x 2 are also independent, they are also independent. So, general solution of x dash is equal to, for this system Ax, I will have your capital X t is equal to something C 1 times x 1 t plus C 2 times x 2 t, where C 1 C 2 are constant over the corresponding field, say capital F, where C 1 and C 2 are constant from the field capital F. Over here the system is defined please. So, I got this general solution of this system x dash equal to Ax like this thing. But friends, I have mentioned that here minimal polynomial of A is x plus 2 whole square. Okay. So, P is equal to x plus 2 whole square, and I see that, which is also characteristic polynomial here. Also we see that when you consider P of A, this is operator. Now, P of A operating on U equal to 0 and P of A operating on V also equal to 0. U means the eigenvectors, what I calculated U equal to, I have mentioned, that is 1 0 and V is equal to basically second vector 0 1 please. I am not saying that V is eigenvector, I am saying that only U is eigenvector, V is not. So, this implies U and V are in the null space of PA. Here V which satisfies the conditions that A minus lambda I square operating on V equal to 0, but A minus lambda I operating on V is not equal to 0. Such type of vector is called as generalized eigenvector. So, let me define what is generalized eigenvectors. What is generalized eigenvector? Let A be a matrix, be a square matrix, defined over a field say capital F, or let T be a linear operator defined over a finite dimensional vector space V over the field say capital F. Let lambda be an eigenvalue of A. A vector U satisfying the condition A minus lambda I power R operating on U equal to 0, but A minus lambda I power R minus 1 operating on U not equal to 0 is called as a generalized eigenvector of rank R. So, actually this I already have seen that in the solution of the initial field problem, the concept of generalized eigenvector is there. Okay, this is called generalized eigenvector rank R associated to eigenvalue lambda please. So, if U is an eigenvector associated to eigenvalue lambda, then U is called as a generalized eigenvector of rank 1. Now, let us see, if I consider a vector, generalized eigenvector of rank R, I will show that it introduce R vectors which are linearly independent. Let U be a generalized eigenvector of rank are associated to eigenvalue say lambda. So, this implies A minus lambda I power R operating on U equal to 0, but A minus lambda I power R minus 1 operating on U is not equal to 0. Consider V R equal to U, which is equal to, I can write down A minus lambda I power 0 operating on U. So, we have V R is equal to U is equal to A minus lambda I power 0 operating on U. Then define V R minus 1, which is equal to A minus lambda I operating on U, and V R minus 2 I am defining as A minus lambda I square operating on U, and so on. I can consider V 2 is equal to A minus lambda I power R minus 2 operating on U, and V 1 will be equal to A minus lambda I power R minus 1 operating on U. So, I have introduced R vectors V 1, V 2, V R. We have A minus lambda I operating on V 1 according to my definitions from the above. This is equal to A minus lambda I into A minus lambda I power R minus 1 operating on U, which is equal to A minus lambda I power R U. So, we have A minus lambda I operating on V 1 equal to finally equal to 0. This is equal to 0, because we know U is the vector satisfying A minus lambda I power R operating on U equal to 0. So, this implies V 1 is an eigenvector, So, what can you say about V 2? Will it be eigenvector? No, V 2 cannot be, because I will not say that A minus lambda I operating on V 2 will be equal to 0. You can see it, please. So, you will see that that is equal to some non-zero vector. So, V 2 cannot be an eigenvector. However, this V 2, V 3, V 4 even including V 1 up to V R, they are basically generalized eigenvectors. So, we have R generalized eigenvectors, vectors V 1, V 2 and V R, please. If I consider A minus lambda I power I into V I, so what can we say about these ones? A minus lambda I power I operating on V I. So, I basically if I consider from 1 to R, then this is equal to V 1. you can check it, this will be equal to V1, because Vi will be according to this formula R minus I, because we have A minus lambda I power I into Vi will be equal to A minus lambda I R minus I operating on U. Okay. So, this is equal to A minus lambda I power R operating on. So, I think that is 1 is missing, I minus 1 if I consider, Vi will be equal to R minus I. So, it will basically R minus 1. So, this is equal to V1 please. So, A minus lambda I power I minus I when operating on Vi equal to V1 please. Anyhow, so this is some relation I am getting please. So, for a generalized eigenvector of rank R, we have seen there are R vectors. We have from this R vectors, we have Vr equal to U equal to A minus lambda I operating power 0 operating on U, and Vr minus 1 is equal to, we have defined A minus lambda I operating on U. So, this is equal to, I can write down A minus lambda I operating on Vr. So, Vr minus 1 related by Vr like this. And what about Vr minus 2? Vr minus 2 is equal to, according to these definitions and my last analysis, I have seen that A minus lambda I whole square operating on U. So, this is equal to A minus lambda I into A minus lambda I operating on U, which is what? This is equal to Vr minus 1. So, Vr minus 1. So, Vr minus 2 related like this. So, in general I can say Vi minus 1 equal to A minus lambda I operating on Vi, and the V1 equal to A minus lambda I into V2, and 0 is equal to A minus lambda I operating on V1 please. So, if I consider V0 is equal to 0, then I have this type of relations. So, this implies that, this implies for V0 is equal to 0, I can write a relation like, you know, Vi minus 1 equal to A minus lambda I operating on Vi. For I equal to, I can say 1 to R. So, I have R vectors, generalized eigenvectors from the generalized eigenvector U of rank R. This is called the, I mean, this gives a R vector, this is called the chain of generalized eigenvectors of length R. So, the set V1, V2, Vr is called a chain of generalized eigenvector of length R. So, we see that if we consider a generalized eigenvector of rank R, it introduces a chain of R generalized eigenvectors V1, V2, Vr, where V1 is eigenvectors of rank 1, you can say. I am giving to you that proof that this chain of R vectors are linearly independent. Consider it as a homework please. We will continue this in next class also.